not one accepted algorithm. There were 3 algorithms for subtraction in the 40s. They included decomposition algorithm, which is the borrowing algorithm that we all know and love. The equal additions algorithm, which we will talk about, also known as constant difference. And then there is the Austrian algorithm, which is the count back change method, starting from the small number and counting up until you get to the larger number. A lot of people want to ask why we have to teach math differently now. Didn't the old way work just fine for us? And I just would challenge you to wonder, what is your relationship with math like? Do you love math? If you do, ask yourself why you love it. What is it about math that you love, and how did that get fostered? How did the love of that get fostered? A lot of times people are very willing to say how much they hate math, but yet if you asked them, and they would say because they're not good at it, but if we are honest, no one would ever say that they're not good at reading or they can't read. So I would just challenge you to be careful about how you talk about math in front of students. If you're watching this, you're probably a parent, and you're trying to help your kid, which is so respectable, and but yet we just want to be careful about how we talk about math, because we want our kids to think that they are good at math. So we're going to jump into some subtraction strategies. All the strategies that we're going to talk about today fall into one of 3 categories. They're either a place value parts category. In this case, you might hear it, your kid's school might call it tens and ones, or they might call it place value or something like that. But it's where we're going to break up and subtract each of the place value parts. Another strategy kind of taken from that is called incrementing, where we keep one number whole and we break up the other number into parts. And then the third category would be called constant difference, which is similar to the addition strategy of compensation, if you've watched the addition video, but it is how we make easier problems using subtraction. So tens and ones would be the strategy we're going to start with. And if we were trying to subtract 38 from 91, the way we would do that is we would break up the two-digit numbers into their tens and ones place values, and then we would subtract. A lot of times teachers may even ask students to write it like this, and then they would have students subtract this way. And the correct way to do this, you can see on the screen, is to, and a lot of kids want to think about tens place first. They would say 90 minus 30 equals 60. And then the problem becomes, on this problem, that we want to subtract the difference between 1 and 8. And some people would say, well, you can't do that. And the truth is that you can do that. If it is 1 degree outside, can it get 8 degrees colder? Sure. Not in Alabama, maybe, but in Minnesota, it can. If I have $1 in my bank account and I run my debit card for $8, unfortunately, my bank allows me to do that. And then I just get this red alert on my account that now I'm in the hole, and then I have to pay them more money for overdrawing. So we want to be careful about saying you can't take a bigger number from a smaller number, but we want kids to understand that you can. It just results in a negative number. So you can get colder than 1 degree. It just means you're going into the negative degrees, right? And this is a really difficult concept. Second graders are going to really struggle with this idea, this backwards thinking. Subtraction is hard enough because it is a backwards thinking. And then to add in this idea of negative numbers, because what really happens is you get 60 and you get a -7, but you have a plus here, right? And you may remember when you were in middle school that your middle school teacher may have taught you that plus and negative is the same thing as saying subtract. So the correct answer is 53, but the most often incorrect answer for this problem is 67, because kids don't understand this signal right here and they just put the 2 values back together. So this is called place value, or subtracting using tens and ones, but we want to be careful about overgeneralizing this concept to work all the time. With the first problem that we have here, I'd like for you to take a minute and try subtracting using tens and ones. And if you need more time, feel free to pause the video. But real quick, it would look something like this. And with this problem, it works beautifully, right? Okay. Now take a second, pause the video, and do the next problem. Okay, if you need more time, feel free to take that. But the way that students might do this is to literally break up the entire place value. Okay, but that can get tricky, right? What may be easier, a better way to do that might be to chunk only parts of this number and subtract that way, but you're still going to find students are counting backwards using their fingers or some other strategy to figure this part of the problem out. So you'll notice that it works great with a problem like this, where all the digits in the top number, so to speak, are larger than all the digits in the bottom number. But as you get into some more realistic, harder subtraction problems, you're going to find that this strategy is going to fall apart for kids if they don't understand how to deal with negative numbers. And you're going to end up with a lot of negative values having to subtract each part like that. So this strategy can be helpful, but it is not, we don't want to leave kids in this strategy. We want kids to understand some more generalizable strategies. The next strategy we're going to talk about is kind of a combination, or kind of is using some of those ideas of breaking a number apart. But in this case, we're going to keep one number whole and subtract the other in parts. Oh, I did want to say this. On this strategy, the tens and one strategy, the model that kids are going to use to look at this is going to be typically a place value block strategy. So they might draw something like this. And this is the base 10 block or place value block strategy to model 69. So each of these sticks is worth 10 and each of the dots is worth 1. And then to subtract 45, they're going to have to go, okay, take away 10, take away 20, 30, 40, 41, 42, 43, 44, 45. And then they would put this back together to find out what's left. This is the physical model that would go with this strategy. And you can tell when I look at what's left, when I look at this model, it's hard to really see the original problem inside of this model. So this model can be a little bit tricky for kids to get used to or to deal with, which also further complicates the strategy. On this one, the model that goes with this strategy is a number line. We're going to keep one number whole. We're going to subtract the second number in parts. We're going to keep the top number or the first value whole in this case. So we're going to hang on to 91. We're going to start at 91 on a number line, and then we're going to chunk the next number. So in this case, it's easy to think about it as a 30 and an 8. So we're going to take away 30 first, and then we're going to take away 8. And kids learn to count off the decade by tens, meaning to count forwards and backwards when there is a non-zero number in the ones place, and they understand that adding or subtracting 10 to any number only changes the tens place because there's a zero in the ones place. So this is not terribly far off. Some kids might look at 91 minus 30 and be able to just say it's 61. Some kids may need to look at 91 and take away 30 by doing 3 chunks of 10, and they would say 81, 71, 61. Okay, so that's the take away 30 part. Now we're going to take away 8, but we're at 61. And so a lot of times kids can think about 8 and decompose it so that they can get to a friendly 10, and then they just have to take what's left from a 10, and which is why we push fluency to 10. And so they might think about take away 1 to get me to 60, and then I just have to think about my tens partners. I have to take away 8. I already took away 1. What's left to take away is 7. And so what goes with 7 to make a 10 is a 3. So I'm going to take 7 away and land at 53. So again, this can be done also just with numbers without a physical model, and it would look something like this. Okay. Let me erase this. All right, so I'd like to give you a moment to think about this strategy. So we're going to try the first one. So feel free to pause the video while you work. I'm going to go ahead and jump back in and think about 69, and we're going to take away 40 and then 5. So we're going to first take away 40, and when we jump back 4 tens from 69, we're going to land at 29. Okay, because again, the tens place is the only thing that's having to adjust, and it's adjusting by 4. And then we do 29 minus 5, and we can just know that that's 24 if we know something about those combinations. Okay. If we're doing that same idea with these 3-digit problems, go ahead and pause the video, take a minute to try it with 123 minus 107. We're going to do it like this. We're going to hang on to 123, and we're going to subtract the hundreds place, okay, which is going to leave us with 23. And then we're going to subtract 7, and we need to subtract a total of 7, but I'm going to think of my 7 as a 3 and a 4 so that I can get to some friendly numbers. So I'm going to first subtract 3, and that will give me 20, and I still need to subtract 4 more to make a total of 7 that I'm subtracting, and so that's going to land me at 16. All right. And then with this last problem, 3,124, we're going to do this one also in chunks. So first we're going to subtract 1,000. Then we're going to subtract the hundreds place. And what we're going to find here is that we may need to think about this as a 100 and a 200 to get us to let's think, 100 would be 2,124. And then 2 more hundreds would be 1,824. And then we would take off the tens place. And again, we might need to break that up into a 20 to get us to 1,804 and a 40 to get us to 1,764. And then we're going to take away 7. And here we go again, right? We're going to jump back 4 and then jump back 3. And that would give us 1,757. Okay. So you can see this strategy is a quick strategy here. It's still pretty quick here, but what begins to happen is even this strategy, while it's better, quicker, more efficient than the first strategy, it still can get cumbersome as we are subtracting these larger numbers, okay? We want kids to understand the basics of what does it mean to subtract. Subtract means there's 2 types of subtraction. It can mean take away, or it can mean find the difference or the distance between 2 numbers. So we want kids to think about and understand what is subtraction when they're in 2nd and 3rd grade using numbers like this. And you're going to see a lot of this strategy in 2nd and 3rd grade. But there's a reason we have a US standard algorithm that includes borrowing. It's a quick way to subtract. It's a shortcut to subtraction. But kids can't understand the shortcut until they understand how to compose and decompose numbers. So this is why the current Common Core, or in Alabama, the Alabama College and Career Ready standards, are going to really push on some of these other strategies first. We don't get to the standard algorithm until 4th grade. So we want kids in 1st, 2nd, and 3rd grade to really understand what is happening with subtraction before we give them a shortcut to just know how to subtract. The third way we're going to talk about subtracting is using what's called the constant difference. And the constant difference is going to give us a friendlier problem. So 91 minus 38 is tricky. There's borrowing involved. It's or regrouping is the correct mathematical term. And it can get really hairy. So I had a student when I was a 5th grade teacher many moons ago. His name was Vincent. And Vincent told me that he liked to get as many 9s in the top number as possible. After I understood Vincent's strategy, I realized that you can adjust either number to make a friendlier problem. And I actually prefer to get as many 0s in the bottom number. For the same reason Vincent wanted 9s, I want 0s. Because if you have as many 9s in the top number, there's no borrowing or regrouping needed. If you get as many 0s in the bottom number, again, there's no borrowing or regrouping needed. So, so for this problem, we could think about, for Vincent's way, we're going to think about 91, and Vincent would not want to do 91. He would take 2 from 91 to make a new top number of 89. And he understood on a number line, which is the image here, although Vincent would have adjusted in the other direction. He understood that the blue distance here is the distance between 91 and 38. And he understood that if I adjust down 2 to get 89, and I adjust 38 down to get 36, that I haven't changed the distance. I haven't changed the space between those two numbers. I've just adjusted where that space is located on the number line. So instead of 91 minus 38, Vincent would have solved the problem 89 minus 36. Again, no regrouping needed, quick answer. Okay, I like to get as many 0s in the bottom number, so I'm going to adjust 38 to be 40. So I'm going to adjust up 2, so now that's the pink line, and therefore I'm going to adjust 91 up 2 as well, and that's going to give us 93 take away 40. Again, same distance, just new numbers, still a distance of 53. So one thing that we want to look at when we're thinking about this strategy, I will say real quick that oftentimes some people will only adjust one number on this part and then adjust their answer. So for instance, some people will say, oh, 91 is about 40. It's 2 extra, right? And they're thinking about this. I've added 2. So my answer 51, I need to add 2 more on this end to keep it the same. But I have a hard time holding on to if I added here that I add here. So for me, it's easier to adjust the 2 numbers in the original problem. So when we were to practice this, if we were to practice this, we want to think about some things that are important. So when you look at these values, feel free to take a minute, pause the video, and try it with any of these values. What I do want to talk about is you'll notice the numbers, some of the values I changed. Why do you think that is? Number one, if the original problem that we were practicing was here, right, there's no need for any adjustment. Vincent would say that he already had as many 9s as he could get in that top number, so he didn't have to do anything different. So I wanted you to practice. So, but you'll notice, which of these 2 values would you adjust? It's closer to adjust the 61 and just take 2 from each of these values to make a new problem of 59 minus 43. Than to add 5 to both of these values, 66 minus 50. But you can do it, okay? As you get into some of these larger numbers, you'll begin to see where you would have to subtract a lot or adjust the values a lot. Okay, this one, if you just adjust down 1, you're going to get 22,999, right? And then which is a much easier problem. That's going to help you. But the original numbers that I used are difficult, would be difficult. I can't remember. Let's see if we can go back. Trying it with this one. This is a lot to have to subtract off to figure out an easier problem for this one. So what we want kids to understand is not just all the different ways to subtract, but when is it a good idea to use this strategy versus when is it a good idea to use another strategy. So for instance, we saw this strategy with the incrementing or keeping one number whole and subtracting the other in chunks. But if we really think about this number, the best strategy for this problem is probably to borrow, to go over here and rename that. And then you're going to end up having to go back over here and rename, right? And then you're going to go over here and rename. And what kids don't understand developmentally until usually sometime in 4th grade, maybe closer to 5th grade, is that when I've renamed this number, what I really still have is now I have 2,000, and this is 10 hundreds, which is 1,000, and this is 11 tens, which is 110, and this is 14 ones. That if I put all this back together, I still have my original value of 3,124. I just have it in different denominations, so to speak. If this were an amount of money, I could have these bills in my wallet. Right? But students don't understand that early on. And so we're building that understanding by using some of these other strategies, an understanding of place value and an understanding of what's happening to the numbers. But once I understand that this is still 3,124, I just have it written in a different value, then I can understand that I'm going to subtract 14 ones minus 7 ones, 11 tens minus 6 tens, 10 hundreds minus 3 hundreds, and 2,000 minus 1,000, and get my answer of 1,757. So this is where we head for kids in subtraction. We do get kids to this US standard algorithm, which we might refer to as borrowing or regrouping. But we want kids to understand the math that's inside of subtraction. And so we want kids to really value an understanding before we get to a shortcut. So if you have questions, feel free to comment on the video and I will be glad to respond. And hope you have a great day.